Hello, I'm Tim Weaving, a PhD student at University College London, and I'm pleased to welcome you all to the 15th instalment in CompBioMed's e-seminar series in collaboration with the Virtual Physiological Human Institute, or VPHI. The talk today will be given by Brian Wylie, a scientific researcher who has been with the Jülich Supercomputing Center since 2004. He joined the group developing the Scalability toolset for scalable performance analysis of large-scale parallel applications and provided associated support for application developers. He established and continues to contribute to training activities of the Virtual Institute, High Productivity Supercomputing, or VIHPS. His current focus, and the topic of this talk, is the assessment of exascale readiness of applications comprising very large numbers of processes and threads within the Performance Optimization and Productivity, or POP, EU Centre of Excellence in HPC. The title of Brian's talk is Performance Optimization and Productivity Services for HPC Application Developers, in which he will introduce us to the POP COE and review its successes, with particular focus on services provided to CompBioMed and its flagship codes in preparation for upcoming exascale computer systems. Now, before we begin, I'd like to briefly remind you that this session is being recorded and will be available on the CompBioMed website and YouTube channel shortly. So please do use this to go back over parts of today's talk and others in the series, and maybe even share these e-seminars with your friends and colleagues. There will be a Q&A session at the end of the talk, so please save your questions until then. Once the talk is finished, you can post your questions in the questions section, and I will read them out to Brian to keep the session running smoothly. Now that's everything from me. I hope you enjoyed today's talk, and without further ado, I'll hand over to you, Brian.
Thank you, Tim, for that introduction. I hope you can now hear me. I'm Brian Wylie from Jülich Supercomputing Center, which is in the west of Germany, between Aachen and Cologne, for those who know the area. And as Tim said, I'll be talking about the Performance Optimization and Productivity Center of Excellence. We're currently in the second phase of that Center of Excellence, which is started in 2015 and running through to the end of this year. So the Center of Excellence for Performance Optimization and Productivity was set up to promote best practice in parallel programming and the use of parallel computer systems. We recognize that improving parallel software can add a lot of value to it. It reduces the expenditure of using that software. You get the results potentially faster, or you're able to solve problems that you weren't able to solve before and get new results. To do this, we have developed a systematic approach to performance analysis and optimization that builds a quantitative view of parallel application execution behavior that we call our POP methodology. And that's what is going to be the introductory part of this presentation, and then we'll get into a couple of examples of that where we've worked with applications of CompBioMed Center of Excellence. The COE services are free services for academic and industrial users based in Europe, not just within the European Union, but the UK and other associated countries as well. And there are two primary services we offer. One which is a performance assessment, where we provide suggestions on how to improve code performance. And the more comprehensive service is some prototyping and a proof of concept, where we work with you to provide practical help with refactoring, not necessarily of the entire code, but of a kernel or part of it, where we can demonstrate the recommendations that have been proposed. In the team, we have 8 partners. They're ourselves in Germany, and Jülich Supercomputing Center, a couple of other centers in Germany. The coordinator of the Center of Excellence is Barcelona Supercomputing Center. We have other partners in France and in the Czech Republic. Together, we provide experience and excellence in developing and using performance tools and application tuning, the programming models that are used for parallel computing systems, as well as working with applications in a real practical sense. So it's a very diverse team of people working together in the Center of Excellence. I've been working in this field for half of my life, and I still find that understanding parallel application execution performance is hard. There are many ways of doing it. There's lots of tools that are available, but it's a really challenging problem. And it doesn't necessarily get any easier, it just gets worse as you add more complexity, more processors, more threads, more combinations of different programming models. Fundamentally, we recognize that performance can be characterized by the execution time of an application. And so you may look at a chart such as the one on the left-hand side here, which is a scaling chart showing how execution time, or in this case speed up, compared with a reference, a single node here, how that changes as we add more nodes here. If the application was scaling perfectly, we would expect an 8-fold speed up as we have 8 times the number of nodes. Typically, you'll have some fraction of that, and in this case, where you're only getting a 3-fold speed up, the benefit of using those extra nodes has been substantially diminished. So this indicates a problem here. It's not a very efficient execution scenario, but what's the cause of that? Well, to figure that out, we'd have to look at things in a lot more detail. And there are many tools available for parallel profiling, and there's an example here in the middle, or parallel execution tracing, where we can actually see a detailed event by event history of what's happening on each process and thread. So there's very large amounts of data that we can collect, and even by distilling the trace pictures down into profiles, we still have lots of information, lots of metrics about different processes and threads and their execution. So this is potentially overwhelming, and we need to formalize how we do it and provide some structure to how we do that analysis. So the solution that we came up with in the POP Center of Excellence was to define a set of fundamental metrics that can help us to quantify and understand an application's parallel execution, and we can get this the basic data for these metrics from our measurement tools, whether they're profile or trace measurements that we collect. So by collecting some fundamental measurements, we can then determine these fundamental efficiency values, these efficiency factors that help us characterize execution performance and identify what are the specific causes of poor execution behavior. They help us identify the causes of poor performance, and by refining where they're applied, we can then figure out whether they're happening in certain parts of the application execution or subsets of the processes or threads are affected. So they're a very powerful set of metrics that we can apply, certainly as a starting point, but also as we continue the measurement process. On this slide here, I'm showing some of the basic metrics, the ones that we actually started off with that quantify the efficiency of an MPI application, a multi-process application. The blue ones here on the left-hand side are looking at the parallel efficiency, where we are looking at how the different processes and threads are working together in parallel. Parallel efficiency we derive by combining the load balance, how the computational work is distributed across processes and threads, with the communication efficiency, how they interact with each other, how they communicate and synchronize. And then we can also break out the communication efficiency into parts which are related to serialization effects, where there are dependencies between processes and threads that result in waiting time versus the actual fundamental cost of transferring data and synchronizing those processes. So by combining these different metrics together, we build up a hierarchy that together define the parallel efficiency of the configuration that we're executing. The orange-based metrics on the right-hand side are scaling metrics that allow us to compare how performance changes as we increase the number of processes, threads, compute nodes in the problem that we're solving. So things like the instruction scaling characterize how many additional instructions are being executed. If we're executing additional instructions, that has an impact on our ability to scale. But it's unavoidable as we're dealing with boundary conditions and things that change with scale. The HPC scaling is the instructions per cycle. This is a measure of how effectively the processor is able to execute those instructions. And we may also have a third factor that comes into play from the processor frequency. If we are using all of the computational units, then we may not be able to run the processor at the same speed, and it may have to run at a slower speed that will have another impact on how the the performance of the application scales. So we have different scaling factors that are all relative to a base configuration. That could be a single process, but typically it's the processes running on a single compute node. And then we can compare how the execution performance changes, how the scaling changes as we use 2 nodes, 4 nodes, 8 nodes, or as we go up to many hundreds and thousands of nodes. Combining that scaling factor with the fundamental efficiency, the parallel efficiency, gives us our global efficiency that characterizes execution and how it changes with scale. Lots of different metrics. They're not all important and relevant in every case, but even for a fundamentally simple MPI application, they can help us characterize and understand how efficiencies change with scale and where the major inefficiencies are. This fundamental model is one that we've been building on and expanding on to look at multi-threading in various forms, to combine multi-threading with MPI, to factor in GPUs for accelerators, and we also know we need to factor in the efficiency of file I/O, vectorization, and other factors as well. But these are a set of basic metrics that we've been using in POP for some time. In POP, we have a number of open source tools that are coming from the different partners. I'm not going to have time to go into all of them in detail here, but just to mention that there's tools from Barcelona, such as Paraver Extra-E. There are the tools that we have developed and work with in Jülich, which are Scalability, SCORE-P, and CUBE, which is our presentation tool. There are also tools from other partners, Macau and PyPop. Those are all performance tools. Tools not listed here are looking at correctness checking of MPI and OpenMP multi-threading. So those are coming in from yet more partners of the Center of Excellence as well. So these are the fundamental tools that we tend to use. There are other tools that provide the same sort of information as well that can then be factored in to calculate these metrics. An example of the Scalability tool set that is developed in Jülich and the sorts of analyses that it provides here. This is just one example where we're showing that we have a lot of different metrics that are collected typically that are characterizing how MPI is performing, how computation is performing, the amount of data that's being sent and received, etc., and identifying various inefficiencies. Figuring out which of these are the most critical ones and the most important to start looking at is the challenge. And that's why this high-level model of POP efficiencies is something that's a great starting point. We can use the underlying metrics to calculate these efficiencies, and then at a glance, we can see for a particular part of the application execution, what are the major inefficiencies. In this case, we can see that communication is very good. We don't have to worry about that. The factor that's a concern here is load balance. We've only a 0.49 efficiency here for load balance, and so that's the main one we'd have to look at. We can look at a distribution of values across processes here. We can identify that some of them are taking twice as long for this particular execution call path than others. And then by looking at what's happening on the individual processors, we can identify that there's 2 of the processes in this case, and there's something like 20,000 in total, but 2 of them here have much longer execution times than any of the others here. So those are the ones that are the ones in this case responsible for the load balance. So the POP efficiency metrics are a great starting point that help direct how to get down into which factors, which metrics to look at in more detail. Tools like Scalability we've been developing for a number of years now, probably 15 years in total, and in the last years we've been able to use them on very large computer systems, such as the UQueen BlueGeneQ system that we used to have in Jülich, where we were able to do measurements on the full system with, in this case, 1.8 million threads. That's 64 threads on 28,000 processes. But we were able to do the measurements and characterize the execution performance of where the inefficiencies are. Likewise, on the K computer, which was in Japan, again, 83,000 processes there, each on 8 core compute nodes with 8 threads, a total of 600,000 threads in total there. So some very large scale executions. The current generation of computer systems are probably not quite so large, certainly not the ones available in Europe, but we think that we have tools that are ready to be able to assess people's application performance at the very largest scales. Of course, in the Center of Excellence, we're not just dealing with the very largest scales, but also much more modest scales where we have applications running on a single node or just with a few nodes. And so that's why we have, in the Center of Excellence, we've been analyzing applications from a range of sectors here. CompBioMed is probably in the biology sector as we define it here, so that's where about 5% of our services have been done. But we're dealing with a range of programming languages. C++, Fortran are the two most popular ones, but we increasingly see Python coming into play in certain cases as well. And in terms of parallel programming models, MPI is the main one, but we're increasingly seeing combinations of MPI with threading or combinations of MPI with accelerators, and also threads and accelerators and MPI and everything being mixed in together. So these programming models are very diverse as well, and we have to be able to support those in our analyses and extend our methodology to support those as well. On our website, there's a number of success stories that we can refer to where we've looked at different applications and identified and worked on providing improvements, either improving the performance, improving the scalability, reducing the execution time. Depending on the test case, on the application, different metrics are important to the application developers. And the benefits, of course, cover a wide range of scales as well, whether we're focusing on speeding up a single computational kernel or whether we're looking at the execution time of a full-scale application. I don't have time to go through a lot of those in any detail, but those success stories are there for reference, and we're in the process of quantifying and extracting best practices from those to capture those on our website. We capture that information and are making it available as an additional analysis resort for people who are looking at co-design and using that experience in future. Two specific examples where we had detailed information about return on investment. One case which was using the old Archer system, which has recently been decommissioned. We were able to get a 72% faster time to solution. That meant that we could save roughly 15 euros per execution run. And because this application was being executed a lot on the Archer system, based on the monthly usage data that's available, that's a yearly saving of over 50,000 euros. A second case was for a commercial customer who had their own cluster, their own resources. There we were able to get a 62% improvement in the application execution time. That reduced their yearly operation cost by 20,000 euros. And so the benefit in the time which they spent, the 2,000 euros in applying the recommendations, results in a substantial return on investment of roughly a factor of 6 in that case. So those are a couple of abstract examples, but I want to just look at a couple of examples quickly coming from the Computational Biomed Center of Excellence, because I think that's the main focus of interest in this webinar and in this group here. So I'll look at the HemelB application, which was a CPU-based application, but has now been also run on GPUs. And if there's time, we'll also look at a second application called SCEMa, and a third code called Alia has also been analyzed, but I don't expect to have time to cover that in this webinar here. So HemelB, this was a topic of a webinar, I think it was last year, or at least it's a little while back in this webinar series. It's a fluid flow simulation looking at very complex geometries such as those found in the human arterial system. And so a specific example which I was looking at was the circle of Willis, which is the complex set of arteries within the brain. We were dealing with a very high resolution simulation of 6.4 micrometer lattice resolution, so it's a fairly large data set of over 10 billion lattice sites. And that simulation we were able to run on the SuperMOOC NG system, which is one of the tier 1 computer systems in Germany, and look at it scaling basically up to the full size of that full system, up to 300,000 and more processes. When I look at the scaling of that application, which is the solver part here, the simulation part in green here, we see that it's actually scaling extremely well from the smallest configuration here on 18 compute nodes all the way up to 300,000 processes. The scaling is tailing off a little bit, as you expect at the largest scales, and that's just because we're running out of computation as we use more and more processes. There's just a little bit less work for each process to do, and that reduces our efficiency. But we're able to see a great speed up over that scale, up to a factor of 190 on the full system there. So by going from 18 nodes up to the full system, that's 190-fold speed up. To quantify and understand the execution efficiency, we're using these POP efficiency metrics. If I start off by looking at the efficiency on the smallest configuration here, which is for 24 nodes, so that's our reference execution for computation. But we see that the communication on those communication efficiency is excellent there, and that communication efficiency stays excellent all the way up to the very largest scales. On the other hand, the load balance is not so great. I mean, it's a challenging problem to partition this grid, to actually partition it even on 24 nodes, 1,000 processes. And luckily, the load balance doesn't get so much worse as we go to larger scales. It's a bit up and down depending on how the load balancing works. But load balance is really the major factor that affects most of the scales here. Our reference of a single node for the computation there is great all the way up to 200 or 300 nodes, and then we start seeing that the instruction scaling is the factor that's coming into play in reducing our computation scaling here. So those instructions are just extra instructions that are being executed to process the boundaries, to pack and unpack messages, and because of that extra cost, our scaling is diminishing, and for the very largest configurations here with over 300,000 processes, that's really dropped our efficiency scaling by the highest factor there. So that's not something that we were able to compensate by with the IPC. The instructions per cycle was actually improving at the larger scales. Things were fitting better into cache, and there were less memory stalls accessing memory. But that combination was still not able to compensate entirely for the additional instructions being executed, and so the computation scaling really shows that we have reached the limits where we can effectively scale efficiently here. But what we actually discovered, not only that the code can execute very efficiently, were that there were cases where the execution efficiency was much, much worse. And so one example here was a case where this is a much smaller configuration. This is actually on 15,000 processes here. Again, communication efficiency is excellent, but the load balance is only 50% here. So that's much worse than we were seeing in the previous cases. And when we try and figure out what's going on here, we can see that just one or two processes are affected, and that's highlighted in this chart here, where I'm trying to show what's happening on all 13,000 processes. The ones with the low values or relatively low values are yellow. The ones with the high values here, like this one, are shown in red. And in this case, it's memory stall cycles, stalls accessing memory that are affecting just one core here, one process. And this is an artifact of the processor. It changes from run to run, so it's not something that's easy for us to work around in the application. It's a processor-specific artifact. We also saw cases where it wasn't the processor that was affected, but it was the memory on a particular node, and so therefore all of the processes on a particular node may be showing inferior performance. And again, when you're dealing with very large configurations, especially for an application here which executes very efficiently. As soon as there's one node or one process that's executing very much inefficiently, it really slows down and affects all of the others. That was the CPU case where we were seeing the scaling up to very large configurations on the SuperMOOC NG system. The code is being developed and targeted towards GPUs increasingly, and so a different version of the code, a development version of the code, is what we were looking at in this second case study. This study was done on our a local system in Jülich called JUWELS. It's a heterogeneous system, but here we were looking at the Volta GPUs, the V100 GPUs from NVIDIA. And there we're running one process, one compute process driving one GPU, because there's 4 GPUs on each of the compute nodes. It's a slightly different test case where we're looking at a wider geometry, which is not just the brain, but is actually looking at the human arterial network. So it's a slightly different configuration, a slightly smaller problem test case that was suitable for testing on the GPUs that we had available here. In this case, we can break out the efficiencies of the CPUs from what's happening on the GPUs. The Scalability tool allows us to see what's happening on the GPUs and which kernels are being executed and which streams those are being executed on, which GPUs are executing those CPU kernels. This is a textual representation. We can show things graphically as well, seeing the imbalance across the GPUs here, which kernels take longer. When the key thing to note here is that not all of the kernels are being executed on all of the GPUs, and that's actually one of the factors in there being a load balance here, that there are certain processes that are dealing with the input and output into the simulation. Those are additional kernels, that's additional work that are being processed on some of the processes, some of the GPUs, and that actually leads to some of the imbalance that we were seeing. Here we're looking at the memory copies, and the color coding here in the middle also shows that the memory copies from the CPU to GPU and vice versa and reverse coming back are again imbalanced, where the compute nodes in the interior of the simulation have much higher transfer times than the others, and that's again a factor that plays into the load balance. A third factor that we identified was the MPI file writing, the writing of state periodically to files. It's not done every time step, but whenever it's done, that file writing is also a major cost, and it's an imbalanced cost as well. So all of the processes are involved in doing that writing. While the writing, there's nothing happening on the GPUs, but the imbalance across processes is also very significant. So all of those factors come into play, and when we're looking at the scalability here, there's lots of different scaling shown on this chart, but the key thing is that the light green curve here flattens off. That's the entire simulation, including the file I/O. If I just look at what's happening on the GPUs itself, these are the dashed lines, those are scaling much better. So there's actually a much better scaling of the GPUs when we look at the performance of those across multiple nodes. Here we're just looking at a relatively small configuration. The cluster that we had available in Jülich had 32 nodes, and so we had about 128 GPUs in these configurations. But this code has now been run on much larger configurations with thousands, I think 18,000 GPUs on the Summit system, where it's also showing good scaling up to 18,000 GPUs. So what we can understand about the performance and its efficiency at small scale directly factors into how to improve performance at larger scales as well. The efficiency metrics that we're experimenting with, we're expanding in POP, they were showing that the computational scaling was relatively good. There was some deficiency here because of the extra processing, having to deal with the fact that the kernels were having less work to do as the application scaled up in this strong scaling configuration. So those having to deal with larger numbers of shorter kernels was less efficient. The load balance across the GPUs is the major inefficiency. it's not so bad on a single node, but as soon as you start using multiple nodes, it starts to deteriorate, and that's again one of the main factors that has to be addressed to have things scaling to larger scales. Here, this inefficiency is probably also taking into account what's happening in terms of waiting for the CPUs when they're doing file I/O as well. Okay, so breaking down what's happening on CPUs and GPUs, this is again looking at scaling from 1 node to 32 nodes. The two charts here are showing what's happening on the left-hand side on the CPU, what's happening on the right-hand side on the GPU. The computation on the GPU is pretty balanced and stays constant as we would expect. What's changing is the idle time on the GPU, and the GPU is having to idle because of what's happening on the CPU. There's more time for communication, there's more time for synchronization, and there's also more time for file I/O. So all of those are negative impacts in terms of how we can keep the GPUs effectively used throughout the computation in these cases here. So all of these factors come into play, and we can break them down and figure out which are the ones that we need to focus on to improve performance. I've got a few minutes to talk about the third case here, which is a composite application where we're combining the LAMMPS nanoscale molecular dynamics simulations, which are being coupled with a macroscale finite element solver. So these are a combination of LAMMPS and DL2. These are two very different solvers with different characteristics, but the LAMMPS simulations are the more expensive ones, and we're doing lots of those. In the test configuration we're executing here, we're actually executing 80,000 of those separate simulations, and actually they're double simulations in 2 parts, but there's roughly 80,000 of them over the 20 time steps here. And so the scheduling and how those simulations are executed is one of the key factors in terms of how this application configuration changes and how it scales. We were dealing with this code in different versions. The original version, we actually weren't able to run on very large numbers of processes. The simulations became unstable, so we had to adjust those to actually adjust the simulation characteristics, the simulation parameters. And this was combined with a major bottleneck where each LAMMPS simulation was, each process was creating simulation directories where it could store log output from the simulations. And so this quickly showed up as a bottleneck where even beyond a few hundred compute nodes, the simulations just were struggling to run at all. We patched those issues and were then able to run up to the full size of the system on the full 84,000 compute nodes. We avoided creating log directories for every process and just have one process in each of the LAMMPS simulation, create a simulation log directory. That substantially reduced the time for that. Likewise, we were able to identify that the communication scaling was an aspect that needed to improve, and by mapping the simulations to compute nodes in a more efficient fashion, where we avoided splitting simulations across compute nodes if we could avoid it. Those are both significant factors in the final version, or the current version, the beta version here, which allows us to scale up and run much faster. So the red scaling here, the execution time decreases nicely for the first from a single node up to 60 or 32 compute nodes, and then it tails off in the original configuration. And then for the very large configurations, we were able to verify that it ran, but the performance is very poor here. Beyond 512 nodes, the performance has deteriorated substantially. In the revised version, we're able to substantially improve that. So we're now able to scale up to roughly 2,000 nodes here. That gives us a 300-fold improvements in performance compared to a single node. Previously, we were only getting a 100-fold improvement. So we're able to scale much faster and get much faster results from these simulations. The story isn't over, but we've already shown a substantial improvement, which is a combined improvement of over 300 for the 300-fold speed up at 1,000 nodes. Again, looking at the scaling efficiencies, we have good performance on a single compute node that deteriorates very substantially where we go up to very high numbers of compute nodes here. Some things are scaling better, so we actually get better file I/O performance if we're running on a few nodes compared with one. But again, that very quickly deteriorated, and for the largest configurations there, the file I/O is really the major bottleneck that was limiting our overall scalability. When we break down the performance and look at the scaling, the original version on the left was showing growing time for synchronization, for communication, and also for file I/O, all of those having a bad impact on the overall execution time, which we hope to have been constant here, or sorry, the CPU time for the total configuration should have stayed constant. On the right-hand side, we've improved it substantially. It's now, we're seeing that the computation time is staying constant. We still have file I/O that's coming in at the very largest scale here, but the communication and synchronization times have both been substantially reduced. Notice the difference of scale here. This is up at scale of 25 versus 90 on the left-hand side. So these numbers are really big improvements over what we had previously there. But at the larger scale here, 1,000 nodes, we still have synchronization and communication, and we still have file I/O factors that are going to limit and do limit the scaling beyond 1,000 nodes here. So we have work to follow up on, and that's what's ongoing work that we're doing in combination with developers in CompBioMed at this point. So we had a series of successes here in terms of getting the code running at large scale, getting an 80-fold speed up in the initial configuration, an additional 8-fold speed up from reducing the number of log directories that were being created, and then at the very largest scale, we eliminated the unnecessary log directories completely, and that gave us an additional factor that improves our scaling. We still have file I/O issues because there's still the results of one simulation are being written and then have to be read back into the next one, which probably is on a different compute node. That means it's in a different file system cache, different node cache for the file system. And so that's likely to be one of the major issues that's coming into play at the largest simulations. And so we need to think about how we can map the simulations onto compute nodes in a more efficient fashion. Not necessarily easy, but these are things that we're looking into. So those are 3 examples which I've gone through quickly of applications where we've been, applications from CompBioMed that have been running at large scale and are running at very large scale of not only thousands of GPUs, but tens of thousands of GPUs, not only hundreds of thousands of CPUs, but many hundreds of thousands of CPUs. So, I mean, these are relatively good test cases for us in terms of what we're doing with other COEs, but we have other examples where we're working with other COEs, with the COE for solid earth, the COE for combustion, and again, we've been looking at their codes and how those codes scale to large scales of many thousands of GPUs and many thousands of processes as well. There's lots of information available for reference on our website. That's also where you can go if you're interested in applying for one of our free services. There's also lots of information material that's available in our newsletter and in webinars and podcasts on our website. A major part of the COE is our training and education program, where we do training for individual customers or in conjunction with COEs, as well as more generally for a wider audience of developers in Europe and throughout the world. We like to combine not only presentation and lecturing with showing people how to use our tools, but actually help them to apply our tools to their own applications. So we encourage people to bring along their own codes to those workshops, and we will work with them to analyze the performance and give ideas for how to improve performance specifically for those codes. These workshops can be relatively short, of 1 or 2 days, up to lasting a full week. For things like one-day tutorials, we typically are not able to work with people's own applications, but those are more focused on introduction to the entire process, how to use the tools and what they can offer. One of the things that we've started in the last year, actually at the beginning of this year, has been a monthly series of full-day virtual training events, where it's taking what we would normally have done in a very focused context of a one-week workshop and spreading that. So it's a monthly installment of these of this training. So that gives people much longer time, much more of an opportunity to take the results of 1 week to rework their code, rework their test cases, and prepare for the next event, which comes a few weeks or a month later, and then apply that additional knowledge and that revised version of the code to the next round of analysis and tuning. So we're experimenting with the different tutorial formats. Most of these are involving recordings, which are available online. There's also additional learning materials which are on our website as well. These are again something we set up at the beginning of this year, a set of short modules of 10-15 minutes explaining what the tools do and how to use them, how to install them. And so those are again additional resources that people can use and refer to in their own time. So I'm running out of time, so just to summarize what we're doing in the POP Center of Excellence, we're promoting best practice in parallel programming. We're incorporating and encouraging a systematic approach to performance analysis and optimization, where we are very much working with application developers, but also training HPC analysts to become experts in how to use our tools and use our methodology. The methodology is based on a set of metrics that help us quantitatively get a picture of application execution behavior, providing a quick diagnosis, but also a starting point for diving into more detailed analyses. We started with MPI and multi-threading, but we are extending that to hybrid combinations and using GPUs and other combinations of more heterogeneous configurations as well. This is an approach which we're applying across a range of scales, across a range of application domains, working with multiple applications and multiple platforms, and available across the community of people based in Europe who are developing applications and looking to have their applications scale and being able to effectively use larger configurations, and particularly those which are coming online and being available in the next years for very large scale exascale executions. So with that, I'll stop here and just put up my my reference slide if you want to contact us. If you want to get additional information from our website, we're very open to working with you. And I'll hand over to Tim and see if he has any questions.
Fantastic. Thank you very much, Brian, for giving us such a valuable talk. Just a quick reminder for the audience, if you do have any questions, then please go ahead and write them in the questions tab so that I can read them out for you. Now, whilst we wait for the questions to start coming in, I actually have a couple myself for you, Brian. So much of the performance analysis is necessarily system specific, right? But say I switch from one HPC rig to another, how much of the analysis will apply for the integration of my code on this new machine, or would I need to come back and request further POP services?
So you're right, Tim. We're doing real analysis of real applications on real systems with real test cases as provided by the customers or whoever asks for the service. So those are necessarily very specific in terms of their performance. But we've tried to incorporate in our methodology an analysis of the fundamental factors that impact the performance. So things like load balance affect your application irrespective of which system it's running on. Serialization is going to affect you irrespective of which system you're running on, and likewise how the computation scales. So it doesn't matter if you use a processor that's 10 times faster or 100 times faster. If it's load balanced, if it's serializing, those efficiencies are going to remain. some of the things will change with scale and with different systems, such as the transfer efficiency, for example. That's based on your network characteristics. So if you go to a system with a faster network, or you're running in a configuration where you use different numbers of processes and threads, then your transfer efficiencies can change. But a lot of the metrics are based on fundamental performance factors that are going to apply across scale and irrespective of the system where you're running.
I see, brilliant, thank you. I'm seeing a question here now. So this is from Peter Coveney. He says, thanks for an excellent talk, Brian. So you've mentioned the importance of improved load balancing for the HemelB application. What is your opinion about the best way forward from here in terms of improvements to such capabilities? That perhaps the all load balancing library from JSC appears to be one which holds some promise. Are there any others you might recommend?
I mean, fundamentally, load balance is related to the problem, and if you're dealing with a challenging load balancing problem like the geometries that HemelB is dealing with, then it's going to be tough to get it perfect, and in many cases you're going to have load balances that change dynamically, that if you have particles moving from process to process, from node to node, your load balances are going to be changing with time as well. So there's only so much you can do with a static load balance, even if it's perfect. That means that you increasingly need to think about dynamic load balancing approaches, and dynamic load balancing approaches are also a great panacea for the fact that the underlying hardware is not necessarily the most reliable and consistent as you might like it to be. So if you're dealing with 1,000 nodes and one of them is having an off day and running 10 times slower, or maybe just 50% slower than the others, then you don't want that one node to be constraining your performance of the others. So being able to compensate for that one slow node or one slow core, depending what the situation is, becomes increasingly important. And that can only be done dynamically. You can't necessarily determine this in advance, or it can be very costly to determine it in advance, and then next time you run it changes and there's a different node that's affected. So so static load balancing approaches are great. They've given us a lot of performance so far, but dynamic load balancing is I think inevitable as we deal with larger simulations and more unreliable hardware in the future. And whether that's dynamic load balancing across processes or dynamic load balancing within nodes where you're using a multi-threading load balancer, both of those have a role to play. And of course, if you start moving GPUs into the mix as well, you have to make sure that you are balancing those as well. I'm not entirely sure that there's so much benefit from using the CPUs, while in most configurations, it's the GPUs where you get most bang for the buck. That's where you need to keep them busy and running effectively. But if you can use the CPUs that are available there, the cores on the CPU side of things, then that has the potential of giving you at least another 10% as well.
Great, thanks for a very comprehensive answer, Brian. I'm not seeing any other questions yet, so I'll ask you another one. And I have to ask this because I'm a quantum guy. But as quantum computing develops and becomes more practical, would the POP COE be able to provide similar support in the future for this fundamentally different computing paradigm?
So I also recognize that quantum computing is fundamentally different, and it's not something that I have very much experience with. I mean, it's becoming more practical, as you say, but I think it's still a long way off becoming used in a widespread fashion, and where you haven't had anyone applying for services so far expecting to use quantum computers. I actually don't really know how people are currently or planning to program their applications on quantum computers. It may be that it's a continuation of the old story. It'll be MPI plus Fortran. May not be recognizable as Fortran today, but it might be still called Fortran, or maybe it's called CUDA, I don't know. But maybe it's something completely different. And I'm not sure that even MPI is going to be so relevant when people are programming quantum computers. But I have to imagine that things like fundamental things like we mentioned, load balance, that's going to be relevant when you're dealing with qubits and quantum computers as well. Computational scaling, I imagine, will be a factor as well. So although I don't have confidence in being able to talk about quantum computers and what will be needed there, I think that by focusing more on these fundamental factors and less on MPI performance, less on OpenMP performance, we're perhaps heading in the right direction.
Sure, I see. Thank you.
But yes, I mean, POP has funding to run to the end of the year, and I'm not expecting there to be too many quantum computers in that time frame. We're of course looking for a continuation of our funding in a third round, and even in that round, which maybe would start next year, I'm not sure there'll be many quantum computers on the horizon in that time frame either. But we know we have to deal with the new systems that are coming, that are using different GPUs, that are using FPGAs. Those are much more of a challenge for us on the immediate horizon.
Right, okay. I have another question from Peter Coveney for you. So with the advent of GPU accelerators in the biggest European machines, this presents a challenge to many applications scientists in terms of porting and scaling, which can then be very demanding. Do you feel that the POP COE is able to provide all the technical know-how to support these people in their various COEs, or could the EU do more to help address this issue?
I don't think that we want to claim that we know everything. I'm pretty sure that we don't. And it's been, I would say, in the first round, the first 3 years of POP, we had very few services that were looking at GPUs. And if they were looking at GPUs, it was a single workstation or a couple of GPUs. It was very, very small scale GPU usage. At least in the second round, we're now looking at COEs in particular, bringing us codes that are running on hundreds and thousands of GPUs. And as I said, this is a learning experience for us, how we can expand that in our methodology, how we can provide the appropriate insight into what's happening on the GPUs and what's the balance of computation between CPUs and GPUs, etc. So we don't have all of the answers. We are building up. We're trying to capture some of those best practices, but there's certainly a lot more that needs to be done. And the other COEs are doing a lot of that themselves, and they need to do it themselves. There's also other centers of excellence started by NVIDIA and others that are looking into this. It's a very big problem, and I think that we need to share our experience and work together to address this very big challenge.
Yes, of course, right. Now there don't seem to be any further questions coming in. So I think this might be a good point to draw the session to a close. Oh, sorry, might be a bit premature in that. One more here. So does POP support MPI plus FPGA accelerated codes?
Not to my knowledge. I mean, I certainly know from the Scholastica side of things that we don't support usage of FPGAs at this point. I know that our partners in Barcelona have been looking at FPGAs and are working with they're involved in the RISC-V design, which is FPGA based, if I'm not mistaken. So we do have partners who are starting to look into FPGAs, but that's still very new, very much work in progress there. And then combining it with MPI, I think, would be an additional challenge, but the MPI part we are much more familiar with.
Okay, I see, thank you. Okay, I think that looks like it's that's it for questions for good this time. So thank you once again, Brian, for giving us your time today to speak about POP services and the important work that the COE does. Just one final reminder that this e-seminar will be available on the CompBioMed YouTube channel and the website, which is accessible via the link, on the link shown on the screen currently. And finally, thank you to everyone in the audience for attending, and I hope you all enjoy the rest of your day.